Hi, everyone. My name is Shoumik. I'm an engineer in the query processing group at Databricks, and today I'll be talking about Photon, a new SQL query execution engine that we've been developing for our Lakehouse platform. And this is work done by dozens of people at Databricks, really, of course, not possible without all of their contributions. So before jumping in, I'll first motivate and introduce Databricks and its Lakehouse architecture. So today, businesses generally store data in data lakes like S3 or ADLS, where they can take advantage of the economies of scale of cloud storage. They can also use frameworks like Spark to load and process data over their data lakes with SQL, machine learning, and so forth. But organizations today also ETL a small fraction of their data into data warehouses like Teradata or Snowflake, for example. These warehouses use proprietary storage formats and claim to offer faster SQL performance compared to just querying the data lake directly. And in reality, a very small fraction of the total data volume actually ends up in these warehouses. And the main reason for this is that it's very expensive and error-prone to set up these ETL pipelines. So the idea behind the Lakehouse is that we can offer the same or better performance as proprietary warehouses, but using open file formats like Parquet, and by keeping the data at rest using cheap elastic cloud storage. One challenge with the Lakehouse is that we can see data that is in any stage of its life cycle. So a Lakehouse can hold clean, structured tables that BI tools can access, intermediary data that has been maybe clustered and coalesced but not denormalized, and also raw data that, for example, uses placeholder strings instead of nulls and has many small files. So we've seen this quite a bit in production. And in such an environment, the burden of good performance ultimately falls on the query execution engine. So the question of this talk is, how do we actually build a query engine that can support these different use cases that we find against the Lakehouse? And so Photon is the new query execution engine that we've built for this use case. It's a new 100% Apache Spark compatible query engine designed for speed and flexibility. And it's already processed millions of queries and petabytes of data from hundreds of customers. And we've seen it provide up to order of magnitude performance improvements in these real use cases. So stepping back for a moment, where does an execution engine even fit into our overall product? So Databricks provides many different ways of submitting SQL queries into the system, such as Redash, which is our SQL UI, jobs, and notebooks. All of these queries, whether they're expressed as SQL text or data frame API calls, eventually end up at a cluster, which is basically a driver node and one or more executor nodes that run an execution framework, such as Spark. And the driver node creates an execution plan for the query and then asks the execution framework to schedule tasks on the executors to read and process data that may be stored in, say, a Parquet or Delta table. The execution engine thus sits at the very bottom of this stack. Its job is to basically take the execution plan produced by the driver node and basically evaluate it over a single partition of the data. And so a lot of things are kind of simplified since we rely on Spark kind of shared nothing architecture. So Photon doesn't need to worry about coordinating with other tasks, for example. It just needs to kind of evaluate a single partition of data. And so until recently, our execution engine was based on the one in open source Spark SQL. And over time, both Databricks and the open source community have done a ton of work on making this engine fast with optimizations such as on-the-fly Java code generation. And this figure basically shows the fruits of these efforts. It plots the speed up from DBR2, this is our internal fork of Apache Spark, from 2016, all the way up to DBR8 last year. You can think of the DBR versions as basically tracking the open source Apache Spark releases. And even though the performance of the old engine has improved by nearly 300% over the last 5 years, there's basically some limits to using a Java-based engine that would be too hard to overcome if we kind of want to leapfrog to the next level of performance. And so why build a new execution engine? Well, this is what Photon, our new execution engine, gives us. By starting fresh and building a new engine from the ground up, we were able to improve our latest Spark-based engine by over 2x version over version, which corresponds to a 600% improvement over DBR2. And so I'll spend the rest of this talk discussing the kind of salient points of Photon's design and also showing its impact on performance. I'll also talk a little bit about how we integrated Photon with our existing runtime and execution engine. So Photon diverges from the existing Spark SQL engine in several ways. There's kind of three major differences. The first one is that we use native execution instead of JVM-based execution. The second is that we use an interpreted vectorized execution model instead of a code-generated execution model. And the last is that we use column-oriented execution instead of row-oriented execution. So another important design point is the fact that Photon kind of plugs into the existing engine. So we can actually move between the two engines if needed within the same query or even within the same kind of Spark task. And so the focus of this talk is going to be on the 2 points I've highlighted here: why we chose the vectorized execution model as the one to base Photon around, and how we integrated with Spark, which is an extremely popular and fairly generic cluster computing framework. If you want to learn about the other 2 points in more detail, please take a look at our paper. So before talking about vectorization, let's talk about how Spark generally executes queries today, or in the past. Interestingly, Spark now actually includes 3 of the kind of mainstream query execution models that database engines have traditionally used. So back in the early days, Spark used to use the Volcano execution model, where we basically pull data between operators using virtual function calls. This was very easy to program, but it was also painfully slow because of the high interpretation overhead. So for each row, you kind of have to make this function call to do any useful work. So to fix this, around 7 years ago, Spark 2.0 added code generation, which even today is one of the most popular modern ways of implementing an execution engine. So with code generation, when Spark gets a query, it actually generates Java code on the fly that's specific to that query. Now, this is very fast because we're kind of building special code for that query. But the problem is that it's also extremely complex. It's not easy to generate this code from a bunch of fragments, and it's even harder to debug both correctness and performance. So for example, if the query compilation time is high, it's not that easy to debug those kinds of issues. So Photon introduces the kind of third, I would say, mainstream execution model to Spark with vectorized execution. So to quickly describe how it works, interpreted vectorization basically goes back to making these virtual function calls to pass data between operators. But instead of doing it one row at a time, it does it on batches of rows that are stored in columnar format. And so each operator can kind of exploit data and instruction level parallelism for high efficiency. So in most cases, it gives us the simplicity of the Volcano model, but also the performance of the code-generated model. So here's a concrete example of the benefits that using a vectorized execution model provides us for a real operator. So say we have a hash aggregation where we need to look up some keys in a giant out-of-core hash table. With vectorization, we can speed up 2 of the steps that are kind of intrinsic to this operator. First, we can use SIMD to compute the hashes of the keys before probing the hash table. And then while actually doing the probe, we can leverage both instruction level parallelism in the CPU and memory parallelism within the memory system to issue multiple loads to the hash table at once. And the performance impact of doing this is significant. Since we issue these independent loads to the hash table, we can do a good job of masking memory stalls. We can also decrease the time spent doing useful work by using SIMD to hash the values and actually evaluating, say, an aggregation function like sum to get some nice speedups. And then there's other tricks you can play for even better performance, like using huge pages to avoid TLB misses. So in our minds, vectorization has kind of 3 big overall advantages over code generation, which is kind of the alternative today of building a modern query engine. So first, the code is just regular C++, perhaps with some templating. This makes it easy to read and debug and optimize compared to writing code that generates other code. So as an anecdotal example, we support this feature called adaptive partial aggregation in Spark. It's not really important what it does here, but with code generation, it took us 6 months to prototype this feature. And with vectorization, I think it took us something like 2 weeks. So second, vectorization lets us maintain the abstraction boundaries between the different operators. This allows us to basically show richer metrics in the UI, for example, since it's easy to see how much time is going into each of the individual operators. And finally, vectorization allows us to adapt to different data on the fly. Since we're basically just running an interpreter, we can actually maintain metadata about each batch of data and pick a code path that is optimized for these particular properties. This is especially important for the Lakehouse since we don't just see these nice, clean world warehouse tables. And you can actually see the paper for more details on specific examples of where we employ this trick. So far, I've talked about the ways Photon processes rows, and in many ways, this is done using techniques that have been pioneered by kind of years of database research. But since this is an industry session, I also want to talk a little bit about how we actually built this new engine and integrated it into a fairly mature existing system. So for the rest of the talk, I'll present our integration of Photon into DBR, which again is our internal fork of Apache Spark. So a straw person approach for building Photon would have been to start all the way from scratch. We basically forced the entire query to only use Photon and maybe just use Spark for task scheduling and other kinds of coordination. This doesn't work for us for two reasons. First, we need to support the thousands of existing Lakehouse workloads that customers have already built using data frames, koalas, PySpark, and SQL. If we were just building a plain database without considering these things, Photon basically wouldn't have any users. And second, somewhat relatedly, we want the ability to kind of roll out Photon incrementally. This means playing nice with the existing engine. So on paper, the way Photon integrates with Spark is relatively simple. Spark has a query optimizer called Catalyst, which allows us to substitute one query plan fragment with another. So at its most basic, Photon is spliced into a query plan using a catalyst rule. And when we evaluate a plan, the Photon parts of the plan just execute in Photon instead of Spark. And adjacent Photon nodes kind of execute without having to go back to Spark. They can kind of run purely in Photon, but the nodes at the boundary need these transition points. So to transition between the Spark and Photon node, we basically add this adapter node that gets inserted over a file scan, which is always the kind of leaf node of a plan. And the file scan in Spark actually already produces columnar data that is stored in off-heap memory or memory outside of the purview of the JVM. So Photon can kind of consume it without copying it. So the adapter node is kind of just taking those off-heap buffers and setting up the pointers so Photon can read the memory on the C++ side. And at the egress point, we actually need to do a pivot from columns to rows so Spark can consume the data. And this does add some overhead, but since the scan produces columnar data, we actually need this conversion even with Spark. So if I go back to the previous slide, you can see that there's this call to row above the scan, even in the original plan. So there's no real additional overhead by doing this in Photon. So one big challenge we faced here is how to ensure that the semantics of Photon are consistent with the semantics of Spark. And in particular, this is important because Photon kind of kicks in as a physical optimization. So we need to make sure that the Photon and Spark results kind of always match. So a few example pain points have been time zone handling, where we need to make sure that we use the same time zone database between Spark and Photon. Integer to float casts. So it turns out that C++ and Java actually have different language semantics for this. And a Unicode handling. So another versioning issue where we need to make sure our ICU library matches the version of the ICU library that the JVM ships with, for example. And the main way we ensured this consistency is by hardening Photon with different kinds of testing. So a few examples are fuzz testing with random data, getting Photon to work with the open source suite of tests that are there in Spark, and also adding different kinds of failure and spill injection to kind of test the failure points as well. Photon supports many other components of DBR. Some examples are spilling, live metrics reporting, and adaptive query execution. I, of course, won't have time to talk about all of these in this talk, but please check out the paper if you're interested in learning more. The main goal of Photon is to improve query performance. And to just show one example of this, we ran the TPCH benchmark with scale factor 3000 on an 8-node cluster with and without Photon enabled. And overall, Photon actually improves the performance by up to 4x kind of end-to-end and by 23x on kind of a single query. So the biggest speed up in this benchmark comes on query 1, which is mostly decimal arithmetic. But many of the other queries kind of speed up for different reasons, such as using a faster hash table and improving expression evaluation time. So you can definitely check out the paper for a more detailed breakdown of performance. And we kind of have these micro benchmarks and all as well to show where you can kind of expect the most improvements from Photon. So just to summarize, Photon is a fast query engine for the Lakehouse. The main takeaways are that it's an interpreted vectorized engine that's fully integrated with Apache Spark, and it's battle tested in production and has shown up to order of magnitude speedups. If you have any questions, I've put the email and also the product page for Photon up there. So feel free to reach out to any of the authors as well. Thank you.